Thank you for coming. Today, I'm trying to introduce or review the paper Attention is All You Need from the perspective of speech recognition because I have experience in it, and my understanding is all based on my daily practice with the attention paper and its derivative methods. And this paper was published, I think, back in 2017 NIPS conference. And before I start with this paper, please let me introduce you another paper before this one so you can better understand it. It's called Listen, Attend, and Spell, aka or abbreviate can be abbreviated as LAS paper, okay? LAS paper for speech, okay. And Neil, can you see my writing?
Yes, I can.
Awesome. And I think this paper was published back in 2016. Archive paper was put online on 2015. Basically, this paper was a derivative of another paper, which is from the NLP domain. The paper's name I forgot. It's more like a sequence to sequence something. It's trying to apply the concept of sequential modeling into the domain of speech. So what is the concept is about? Let me show you this. Remember in the NLP domain, suppose you work on a machine translation task. You want to go from English to French, okay? And then your input sequence, for example, is like a good morning. Mr. Sir, something like this, okay? And this is your input sequence. And your output sequence is like a Bonjour Monsieur or something. Not a French guy. Then you can have this sequence to sequence model right over here. And this is or you can view this as a transducer, and the neural network can look like a black box for you. So all you do in training, you just input this input and output pairs, and during the inference, all you have to do is just send the input into this sequential model. Then you get the output, the inference. It greatly simplified the traditional machine translation modeling technique, which involves rules, model on top of another model, model based upon another model. This is very simple, sequence to sequence model. And the speech guys, they borrow the idea from the NLP, and in this case, it's automatic speech recognition. I used ASR here. And the input this time became waveform, okay. Sorry about my drawings. Doesn't look very good. I wish I can, yeah. This is like recordings, okay. And then you can have this, they call it this is also sequence to sequence model, but I will put the LAS black box here. And they have the output of what? Recognition results, or transcripts, or closed caption, whatever you name it, okay? This, for example, this is a good morning, okay? And you can see this is English ASR. And you cannot to have a English and a French ASR at the same time unless you want to do something. Okay, but I do want to show you how the network structure of the LAS is. So you can see this one. Let me see if I can just draw things on it. Okay, very good. I have it. So the thing is, your recording has lots of inputs, samples. What do I mean by that? Well, suppose you have a speech of 5 seconds. And for speech, people extract the features every 0.01 second. So for 5 seconds, you will have a feature sequence or input feature sequence of size 500, right? I call this D equal to 500, okay? And the dimension wise, if you use MFCC, it could be 13, or you can have filter bank, it's 40 dimensions, okay? But remember, the input length is 500. It's too big, very big. Why? Because for machine translation, you can imagine that usually the input size or the output unit size won't exceed 100, right? Very unlikely for a sentence to have more than 100 words. But the speech, if I talk 5 seconds, I have 500 input. If I talk for 20 seconds, then I will have 1,000. Very big compared to machine translation. And this is why, excuse me, the speech researchers have to develop these pyramid style by LSTM coder. So you can see in this figure, it works. So you can see in this one, after this layer's input got output into the next layer, the two samples got reduced by 1 or 2 1, and the same thing happened to the next one. So suppose you have an encoder of 3 layers, okay? Then imagine what? So for this layer you have a 500. The next layer, your D could be just 250, right? And next layer you can have a size of 125. You can see after 3 layers, the input size got reduced. This procedure is called sampling, or reduce the dimension of the input. I prefer the second, or this is called, a more formal word could be called encoding. Encoding means you want to compress the signal or convert the signal into another format. In this scenario, the encoding compress the signal, okay, by running this type of bidirectional LSTM encoder with multiple layers. Okay. And then you may ask, okay, what's in this case the output is? So the output is, I think in this paper they use the CTC loss or something like this. It can be letter sequence, G space O space, etc. And you can see that the output size is relatively small. It definitely, I think most time it was smaller than 100 too. So they can, in this way, they can plug the NLP framework into the speech framework, and it worked well right now. But although at that time, I think this paper, the performance of the LAS system is like 20% relatively behind the best HMM-based system. But it's very promising, so people start to work on the end-to-end model or sequence-to-sequence model or attention model, whatever you name it, since 2016. And now it's 6 or 5 years from it, and the end-to-end based system is WERS is way better than the HMM based system. But today, I also wanted to introduce another important thing, which I will cover today, which is the attention. So for those of you who are not very familiar with the attention or how the attention is being calculated, I do recommend you to read the paper from the beginning to the end. But today, I will give you a quick, very, very quick conceptual introduction of the concept of the attention, which is being used in the LLS system. Okay. Remember, just call it the encoding, or you can call the bottom part of the LAS system encoder, or the author called it listen. Okay. And then the system also has a module for generating the output sequence, and people call that decoder. And in the LS paper, they also call that spell. I prefer to use the word decoder, and this is being adopted by the most speech researchers. In the decoder, there is a concept called states. I don't think the states has any physical meanings, so you can attach to any of the output labels. But this states, remember, this states is only attached or exists in the decoder. And how many states are there in the output generated or during the decoding that is being generated? Depends on how many outputs there are. Suppose you have n outputs. Okay, suppose the size of the letter sequence is n, then you have n states. N states. And let's look at the back at the encoder. Over here, at each time point, or at each feature you extracted, you have this type of thing called a hidden I would rather not use the word hidden here, although they use the letter H to stand for it. Let's call that embedding, okay? Embedding from the encoder. And you may ask, wait, how many embeddings are there during the encoding process that are being generated? Well, suppose at this final stage, you would have T, I would say T prime embeddings. Or the T depends on how many layers your encoder has. Say you don't have any layers of encoder, the T would be equal to the original D, right? And then suppose you have 2 layers, T would be D over 2. And suppose you have 3 layers, I think the T will be equal to D over 2 to the T to the 2. And then you can see that. And the attention concept, I think you can see the equation over here. See the equation 9 on the left side, okay? Let's see if we can write down this. This equation is one step before I calculate the attention, okay? This is the inner product. And the S is the state. Now what happened? Anyway, the S is the state I talked about. And H is the embedding I talked about. And you can see, in the end, you would generate, a 2-dimensional matrix. Let's call that E. Okay. And what's the how many rows are in the E? It's I, right? X is I. I is the state, right? So it's N by T. And now it's time to calculate the softmax. I don't think it's softmax. I think it's I think sorry, I forgot what you call this. I think maybe this is softmax, yeah. That terminology. This is a softmax. You do it over this matrix. Okay. Then you got another matrix of the same size, which is alpha. Size is N by T. So you may ask, okay, wait, what's the point of this? This matrix is called attention matrix. And this is the stuff, or the most important thing that we're talking about today. And you say that, oh, wait, I'm hearing the attention all the day, but what is attention matrix? What is the attention right over here? Okay, let's look at the equation 11. So in order to understand how important the embeddings from 1 to T to the estimate of the states, let me see the sentence again. To estimate the T embeddings importance to the estimation of the states at time I, you have to use the attention you calculate right now and have a weighted multiplication, the summarization, to get the importance factor. And you can see that because you see that subscript is U, so all the embeddings from time 1 to T are participating in this process. But so let's say at time I, okay, it's a line. Time I, and you may say, okay, at a different time T, the alpha I's value is different. Say at this t, the alpha value is large, and this region is large. But in the other region, alpha start to diminish or get smaller. And if the alpha over the t, which is almost at the end of the sentence, alpha 0 is almost, the value is almost 0, okay? So I'm using the intensity to represent the alpha's value. And then you use this one to weigh. The word is weigh. The importance of the embeddings. Then you got a weighted contextual vector, okay, based on the attention value you calculated. And you use the CI in estimating the states at time I. So where's the equation for estimating the SI? CI is SI, okay. The equation is over here. Okay. So what does this mean? So the estimation, once you get the CI, the estimation of the state is evolved in a Rn process. It needs 3 factors. The CI minus 1 we talked about, and the previous state, and what is yi? Yi is your decoding output at the time I. For instance, suppose the ice output of the ice output is a letter O. This is yi. Oh, y minus 1. I minus 1. I don't care too much, right? It's always the using the path to estimate the current. Then you get the current state. Sorry, my pen is not getting there, but this is what I meant, okay? And once you get the state, remember the state is important in the process of estimating the output y. So where's the equation to estimate or generate the final output y? Equation is sorry, it didn't work. But anyways, it's right over here. Equation 8. I don't know how to get rid of this. I think this is fairly simple. It's a conditional probability, and the input is the state and the contextual vector. You just calculate it. And take the CTC loss, or well, now they call that CTC loss. Okay, the CTC model, I don't agree with it, but people are always call that CTC model. Do I move it up? No. Okay, so you get this PY I given whatever thing, right? At the time I. Then all you have to do is to give all the give the current distribution of the y, okay? So say this is the probability of the py, right? And this is the probability of letter O, letter G, or space character, letter A, letter B, and okay. Letter B is most probable, okay? Then my output is argument marks PYI at time I. Of course, this is given some condition. Of course, then later on you use some letter B decoding because you don't have to make a decision at time I. You can look a few more outputs to make your decision so that, say, the equation equation 16. I think this is a little bit complicated to you, but this is how the language model got plugged in. Language model. In speech recognition, especially end-to-end model based decoding or recognition, usually people use a external language model to apply some extra constraints or domain knowledge for your decoding results. For instance, I have Chinese audience. Let me give you an example, okay? For instance, you can say, my waiter, how much is 水饺? Shujiao means dumplings. But suppose you are a learner of Chinese, then your pronunciation is not very good. You may say 睡觉. This means sleep. Definitely, suppose you have a AI waiter or AI servant or a human servant. She or he would most likely reorder or rescore his recognition result. Even he thought if he only look at or listen to this word, it might sound like you want to sleep with him or her, but he from the contextual language model, he can figure out, okay, you are talking about the dumpling, 水饺, not 睡觉, okay? All right. And then I think I give you a fairly good short overview of the LAS based speech recognition. Neil, any questions? If you don't have any, okay. If you don't have any, I can move on to the attention paper now. Attention is all you need. Okay. I think from now on I will decide to skip the experimental results because I think that's not the most important thing. Because during this tutorial or paper reading session, I wanted to give you the ideas, not to teach you how to do or implement it. Here we comes to the attention is all you need paper. What does paper resolve? It resolves, I think, mainly two things. It resolves first, training speed. Very, very important. Very, very important. Became fast doing the attention-based training. Acceleration of the training. Acceleration. Okay. What's the second thing this this paper, the contribution of this paper, okay? Performance, yeah, or accuracy. It's really good. I have to say it's really good. It's really, really good if you see the results on the machine translation task. Really good. But you can always interpret these two things as one thing, or the most important thing is this one, training speed. Because suppose my training algorithm is faster than yours. That means I can always incorporate more data into my training, and I finish training my model with the same time as your algorithm. And because I use more data, then my model is better than yours, right? So these actually the point one and point two are the same thing. It's all about training speed. So how the attention paper improve the training speed? Let's go directly to the network structure. First of all, I wanna see if I can give you a very quick overview of how they develop their scaled dot product attention. Okay. I think for those of you who have never read the paper Attention is All You Need paper, it might be difficult for you to understand it. But look at the figure 2. It's simple. And then for now, you just have to remember it and try to see whether you can comprehend it. Because for me, even nowadays, I still cannot fully comprehend it. But let me tell you what I think of this algorithm. Remember in the past, yeah, I can move back to my, yeah, this is the paper I talked about, right? Remember just to talk about the attention. So the attention I just talked about was calculated between the embeddings in the encoder and the states in the decoder. So it's coming from the encoder and the decoder. But in the scale dot product attention, the two inputs I talked about in the LAS paper or sequence to sequence paper no longer comes from the decoder and the encoder. It all comes from the encoder. See, first of all, you can see the Q and K. So the Q is called query. Let me see if I can write it down. Just use my mouse to do it. It's better. Query. And another input is called key. But there's no physical query or keys here, remember. And this is just a naming protocol. My understanding is that you can just call whatever you like to call them. And the matmul means the matrix multiplication. Or the purpose, my understanding, is due the correlation of the self signal. Right down here. Okay, this is my understanding. Q times K because you want to get what? Get a self correlation. Which sucks. I forgot how to write it. For correlation, right? And then they pass through a scaling, an optional mask, and they get a soft max. And then they multiply another matrix V. I think this is simple to understand. It's more like scaling. It's more like a scaling factor or something. This is easy to understand. And what does the V is called? It's called the values, right? Values. So I think, in my personal opinion, but although I never tried it, I think the V is not necessary, or not the because, and the biggest beauty of the self-attention paper is this one. This is soft correlation, or the new terminology is called self-attention. Which means in order to calculate the attention, you don't have to wait your decoder to come up with the states. Remember, in order for your decoder to get the states, you first have to wait your decoder to get the output Y, or the output result. And also you have to do everything in a RN transducer. Right? And then you have to wait before you get the next attention at the next time point. Right? But in this paper, all the attention was being calculated in the encoder. There's no decoder evolved anymore. And you say, okay, wait, did this actually accelerate the training? The answer is yes, yes, yes. See the table number 1. First of all, you check the complexity per layer. Self-attention is the dot product, whatever attention, okay? And the recurrent attention, second line, is the attention thing that we talked about in the previous page. And it doesn't go back. You can see that. Remember, the D is the size of our input, right? Most time, especially for speech, I don't know the NLP case. It seems to me that for the NLP case, if you do English to French translation, suppose that the input size is D, and actually the D size is not the input size. The D is actually the representation dimension. So it actually is bigger than the input size. Suppose my input size is speech is T, right? And then at each time point, you have a embedding from your encoder. The size is D, right? So I think the D actually equals to T times D. So you can see D is way bigger than the size of N, which is the output size of the speech recognizer. Usually N is less than 100. Then this one can go easily about 1,000. See, this is why you see that self-attention, complexity-wise per layer, is better or smaller compared to RN. For convolutional thing it takes more computation for sure. Yeah. And then the sequential operation greatly slows down the calculation of the attention. The self-attention, because no decoder is involved, so it's O1, right? Of course, CNN thing, you don't have to wait. It's not recurrent, right? So it's always O1, but this complexity is too big. It's still slower than the self-attention. Okay. And I think this is a side note for you. What's the purpose of positional encoding? I think the author said very clearly. I think they do machine translation, okay? They would say, James does not like Amy. So you can see that in their so-called self-attention or dot product thing, the order doesn't matter, which means suppose you just calculate it on top of these words. In their self-attention, any word to any other words, the distance is always 1. It's different than the traditional sequence-to-sequence model. It's hard to calculate the attention between two very distant location, okay? It's hard to say, for instance, for speech recognition, what's my encoder embedding H1 correlation with the final output, the SD at the very end, right? Distance is too far. It's very difficult. And I personally think it's hard to make sense for this case. How come the first, what I said, correlated with something decoded a final thing, right? And this thing has to be went through a process called RN. Very difficult to learn. Takes a long time. But in the self-attention framework, any word to any words, distance is always considered to be 1. So which means the calculation of the attention became easier, right? Because they use a Q times K. The distance between any words is 1. The word 1, word 2 is always 1. But it also brought a question. Definitely, suppose I write the sentence in this way: Amy does not like Jim. And you see the two sentences are of the different meanings. But in the self-attention framework, these two things would have the same output or outcome. So what do they do? This is why they have to, or they have to introduce some scheme called positional encoding. It's very simple. It just record the absolute or relative location of each word. So say this one is 0 location, this one is 0.1, 0.2, 0.3, sorry, +3. When you just encode the location information into the Q and K, so the distance between words are still 1, but you have this information considered in your model, so your model won't make the mistake of regarding these two sentences as the same meaning. Okay. But the math is trivial. I think you may be confused as why they use these sine or cosine things. I think, my personal opinion, you can use other type of things as long as that you do some positional difference. in the calculation of the output. Not a big deal to me. Okay. And look at the result. I think you have to see the result. It's really, really good. Because if you see the translation task from English to Germany, English to French, these are the best methods or state-of-the-art method back in 2017. And this one you can see it's significantly lifted the bar for the translation tasks. And also, because remember the other methods, they are all using attention between the decoder and the encoder. So their computational cost is high. You can see it's like 10 to the 21 or something. But this one remains or achieves the lowest computational costs, I think, among all, compared to all the other methods. These are all, these 10 to the 19, 10 to the 20, and this is 10 to the 18. And it's got way better result than the other ones. Okay, I do forgot one thing. Because it's a transformer, it doesn't just come with the self-attention. After you calculate the self-attention, what's the overall network architecture? I think it's straightforward, but let me just give you a very quick review. Remember I talked about positional encoding? First, you send input into some input embedding things. It could be CN or DN or multiple layers of a bidirectional LSTM. And then you add the positional encoding into the input embedding, okay? Then here it comes the self-attention thing. And you can see there are three, see that, the three arrows. And this is the Q query, this is the key, and this is the value, okay? And you see this is called multi-head attention. This is easy to understand. What is multi-head attention, or MHA? You will see that very often in the nowadays papers. Or the MHA, multi-head attention. Multi-head. Well, the key is multi. So all the difference is that you see for each V input, it will pass multiple linear projection layers before it got fed into the self-attention layer. Okay, and it definitely has multiple attention layers, right? Calculating it parallelly. Then finally, they concatenate these attention together to form a bigger attention. Why they do this? I think this is not new in this paper because MHA thing is definitely covered in the original sequence to sequence paper. Or in speech, you have this LAS paper, definitely covered. The purpose of this is that in this way, the attention can have a different resolution or different emphasis on different type of things and just work better. I don't think there's a very solid physical explanation of this. And after this got output to the multi-head attention, you just you do this type of resonant connection, right? What is resonant? Snag. Anytime you see a network structure like this, you have a direct pass loop, pass here, and this whatever network is. This is called a ResNet connection, ResNet or structure. This is the invented by Dr. Kai-Ming He. It helps to alleviate the gradient elimination issue. And then this is straightforward. Then you do the feed forward and another ResNet. And then what does the NX mean? You replicate this block for nx times, which means you did this output, okay? Then fed the input into this one, and you get output of the next one and fed it into the input of the third one until you finish all of the nx operations. Then you send the input to the subsequent layers or subsequent blocks. And you can see the left side is the encoder. On the right side is the decoder. And then before we see the cross tension, let's see the decoder first. The decoder, this is autoregressive decoder for sure. Because for either machine translation or speech recognition, the common way of doing the decoder is through a autoregressive decoder, which means the current output at the current ICE output is dependent on the output of the previous one. See, this is why I call output shift right. The previous output got in and went through some CNN or RN stuff, then also added positional encoding here, then pass through a mask multi-head attention. Okay, what does the mask mean here? So for those of you who are not familiar with the speech recognition or machine translation, this might be confusing for you, but it's very easy to understand. Okay. Because it's a autoregressive from left to right decoding for speech, so you always recognize that this. I know next word, it could be it. Okay, to recognize the word it, you have to know the I know first, words first. So during the training case, especially during the training case, so to train on top of the word I, so suppose your current for current training, your YT is no, okay. The training program or the algorithm can only have the access to the words to the left of no. Why? And excluding no word, because suppose the input has the future words or even current word, the decoder will learn nothing. It will all just learn a matrix, okay, which is that whatever you put into in this location, and you output the y, right? But the thing is, during decoding, there's no way for you to know what the output is at the YT. So you have to apply a mask. It's actually a triangular mask, triangular matrix. It's actually with ones on the, it's actually something like a lower triangular matrix of ones. But I guess it's too details. But the only take-home message is that it's try to block the information that the training shouldn't know. So they have this mask. And this is for generating the v vector or the value for the subsequent recognition. And you can see in this multi-head attention stage or self-attention stage, the K and the Q are all from the encoder. So this is different. This is called a cross attention. You may ask, wait, why do I have to have this cross attention? Cross attention. So my understanding is that it's essential and it doesn't hurt. Of course, you can just get rid of this what do you call that? Cross attention by directly feeding this into just put it into this feed forward network. But it lost the capability of connecting the states in the decoder and the embeddings in the encoder. So I think it's smart to have this cross attention. And again, you have this I cannot see this letter. I think it's another N, NX or NY, which means you send the output to the input and you replicate it for N times. Then you get a final output. So Neil, any questions?
Not so far.
Yeah, I think if you can follow me, that means you have some background in the deep learning or attention paper. Very
Yeah.
good. Very good. Okay, I think I will stop here. Let me stop the recording.